Okay, I guess I'll just get started back and then people could come back in. Okay, so if we started to talk about polynomial rings over a field, we've talked about the division algorithm. So let's talk about how every ideal in K of X has to be a principal ideal. Okay. And rings where every ideal is principal of a special name. Okay. So we call them principal ideal domains. So let's take an integral domain. Okay, so if we have this condition, if for all ideals I, there exists A such that I is generated by A, or I is principal, then R is called a principal ideal domain, or just an abbreviation is PID. Okay, and kind of as a consequence of having a division algorithm, we see that K of X is a principal ideal domain. Okay. So let R be K of X, or actually you can do it more generally, like you can, if you can prove this for any ring which has a division algorithm. Any ring with a division algorithm, but for us, it's fine. We can just talk about K of X. Then R is a principal ideal domain. And the proof is just to mimic the proof that every ideal in the integers is a principal ideal. But we're just gonna skip the proof. Okay. But the point is that Now, if you have an ideal in K of X, there exists a generator for that ideal. Okay. So okay. Okay, so let's do an example. So let K be the real numbers. Let I be the ideal generated by x squared plus 1. Okay. Now I have, or let's do capital X, just for some reason. This is an ideal in the polynomial ring with coefficients in R. Okay. Now, okay, and let's take, so the generator for I is this polynomial x squared plus 1. So let's call that F. Okay, so notice F has no roots. Right? Because if you graph x squared plus 1, it's a parabola, like going up away from the x-axis, you know. Here's f of x. Looks like this. It never meets the x-axis. So it has no roots. Okay. And this is, if you're interested in algebra, this is like kind of a problem. You know, this is similar to, sorry, there's a question. Just to confirm, are all 7 questions compulsory? Yes. That is right. Okay. But thank you for that question, clarification. Yep. Okay. So yeah, this is kind of like, we don't like, you know, just in math, like we don't like when things have don't have limits, or when things don't have the least upper bound. That's why we have the real numbers. So you don't like it when polynomials don't have roots. That's why we have the complex numbers, you know. So this is the idea for the construction of the complex numbers. We take this F, which has no roots, and we just invent a field where F does have roots. Okay. So what's our how do we invent a field? Well, move this up. How do we invent this field? It's similar, like we take a quotient. So our problem is there's no, you know, number with f of I equals 0. In other words, f has no root in the real numbers. So our solution is to look at the polynomials in R of x. So the polynomials in x with coefficients in R, and take the quotient by x squared plus 1. Okay, we'll call this, we'll define this to be the field C. So first, why is this a field? So C is a field since x squared plus 1 is irreducible. And we don't have all the pieces for that yet, but since x squared plus 1 is irreducible, that means this ideal is a prime ideal. And from that, you can deduce that x squared plus 1 is in fact a maximal ideal. Now, if x squared plus 1 is a maximal ideal, you take a ring modulo a maximal ideal, you get a field. So that's why the complex numbers are a field. Okay. Now, why do the complex numbers have a root, right? So that this is going to be, so we've defined the complex numbers as the polynomials with coefficients in R modulo this ideal x squared generated by x squared plus 1. I'm going to define a complex number. And it's going to be, in this quotient, it's going to be the coset of x modulo x squared plus 1. So this is a complex number. Okay. And now, how does this kind of solve our problem? Why does this solve our problem? Well, if we look at xi squared, that's just the coset of x times x squared. So it's the coset of x squared. Well, that's just, I can add and subtract 1. So that's just minus 1 plus, I'll just put x squared minus 1 plus, and it's a coset of this. So the coset of I squared is, this coset, the I squared is just a coset of negative 1 plus x squared minus 1 plus, squared plus 1. That's better. Okay. And notice that this is in the ideal. In other words, x squared plus 1 is congruent to 0 mod this ideal. So this is the same as the coset of minus 1. So in the complex numbers, I squared and negative 1 are the same. So you just have the equation I squared plus 1 equals 0 in R of x mod x squared plus 1. Okay. So when I take the quotient by x squared plus 1, I'm saying that we're in the polynomial ring, but now I'm making x squared be negative 1. And when I do that, I kind of invent a solution to x squared plus 1 equals 0. I call the solution I. Okay. So associated to this problem polynomial, which has no solution, well, because it has no solution, you're able to invent a solution. Okay. So no solution in R, that's okay. We can just make up a solution, and we call this. And it is kind of in a way, it's kind of lucky that when you construct the complex numbers, every polynomial with complex coefficients has a root. That is kind of like an accident or something. Okay. So okay, let me also just remind you how the steps of this calculation. Okay, basically we want to show, like we have these two polynomials, x squared and -1 in R of x, and we want to see why are they congruent mod x squared plus 1. So x squared is congruent to -1 mod x squared plus 1. Why is that? Well, the definition is just that this minus this has to be in the ideal. The ideal generated by x squared plus 1. This is just x squared plus 1. Okay. Well, this is the set of all the multiples of x squared plus 1. X squared plus 1 is just 1 times x squared plus 1. So it is a multiple of x squared plus 1. So it's in the ideal. So when we mod out by x squared plus 1, it's like I'm saying, well, work over the polynomials with coefficients in R, but just make whenever you see an x squared, it's just -1. Just pretend it's -1. And we work like that. Okay. And when you do that, you see like you kind of invent for yourself a solution to x squared plus 1 equals 0. Okay. So now I just want to explain a little bit about this sequence of steps, which allows us to take an irreducible polynomial and get out of it, we get a maximal ideal, which means we get a field. Okay. Okay. So first, let's define what an irreducible is, just in general. So let's start with an integral domain, just any integral domain. And now we just take the definition for a prime number and just rework it to work in R. Okay, I think I might have defined this already, but anyways, let P and R. P is not equal to 0. P is not a unit. Okay, so P is not invertible and it's not 0. Okay, so then P is called irreducible if for all A and B, if, or for all A and B such that P equals AB, either A is a unit or B is a unit. Okay. So the only way to break apart P is to, like one of the terms has to be a unit. So in other words, when you try and factorize P, the only way to do it is like PU times U inverse, where U is a unit. So it's like a kind of trivial way. So it's like writing 5 as -5 times -1. Yes, that technically is a factorization of 5, but it's like a not very useful one. Okay. On the other hand, you have a number like 6, that's 2 times 3. Now I really have a non-trivial factorization of 6, so 6 is not irreducible. Okay. So we have irreducible elements. Okay. And first, we can prove that if we have an integral domain, okay, so we want to like kind of develop a relationship between irreducible elements and prime ideals. Okay, so first we have a proposition. Let R be an integral domain. Let P be non-zero element of R, and assume that the ideal generated by P is prime. Okay, so if you start with if P generates a prime ideal, then P is irreducible. Okay. Okay, so let's prove this. It's just kind of like let's see what we have to do. Okay, so P is chosen according to our hypotheses, and suppose P equals A times B, where A and B are in the ring. Okay, and we have to show that either A is a unit or B is a unit. So that's our goal. Now P is a prime ideal. So AB, well, AB is equal to P, and that's an element of the prime ideal generated by P. So a prime ideal is such that whenever you have a product in the ideal, one of the two things is in the product. So now either A is in P or B is in P, since P is prime. Okay. Okay, and now we have to use that to try and prove that either A or B is a unit. And actually, like whichever one is, it's kind of like the same. Like if I argue, like if I do the case that A is in the ideal generated by P, and I do some work and I prove that B is a unit, well, my work can be applied to the case when B is like when I switch A and B. I'm only going to do one case, and that's fine. Okay. Okay. So now let's tackle the case that A is an element of P. Okay. Right. Well, the definition says that A is then P times R, say, for some R. Okay, what does that mean? Now I remember that P equals A times B, and A is just PR. So P is PRB. Now I remember that I'm in an integral domain. And in an integral domain, I have the cancellation law. But P is not equal to 0. That's one of my hypotheses. And R is an integral domain, which means I can cancel. So I cancel the P's. And what do I get? Well, if I cancel P from B, I just get 1. If I cancel P from PRB, I just get RB. And now I have that 1 is R times B. That means that B is a unit. In other words, I've shown that I've shown that either A or B is a unit, and that's the end. So therefore, well, I guess I should really say that the case that B is an element of P is similar. That implies that A is a unit. So therefore, P is irreducible. Okay. So irreducible elements and prime ideal. The converse of this proposition, let me go back up to the proposition. If P is irreducible, it's not necessarily true that P is a prime ideal. You need to add in another condition on R. And, the condition that you need to add in is that you need to assume that R is a principal ideal domain. Okay. So for the converse is not actually true. So let's just look at what is true. So we have another proposition. Okay. After we prove this proposition, we'll take another break, and then after that break, we'll do examples, some different examples, okay? So this proposition, the proposition is that R be a principal ideal domain, PID. Let P be irreducible. Then the ideal generated by P is a prime ideal. Okay. Proof. Okay, so we have to prove that ideal generated by P is a prime ideal. So suppose A times B is in the ideal generated by P. Well, that just means A times B equals RP for some, R in the ring. Okay, and our goal is to show that A is like in the ideal generated by P or B. Here's our goal, and let's try and kind of rework our goal to make it easier. Our goal is to get A as an element of the ideal generated by P. Or another way to write that, our goal is to say that A is equal to P times R. Another way to say that, actually a condition that would imply that, well, this is like saying that P divides A. And then a condition that would imply that is to say that the ideal generated by A is contained in the ideal generated by P, I think. Yes. Okay. So if we prove that the ideal generated by A is contained in the ideal generated by P, then we can prove that A is in the ideal, A is in P. That's our goal. So our goal is to show that A is contained in the ideal generated by P. Okay. So let's define a new ideal. This is going to be the ideal generated by A and P. In other words, this is the set of all things like AR plus PS. Okay, and let's keep our kind of in terms of the goal. If our kind of goal is that the ideal generated by A is contained in the ideal generated by P, Well, if that's true, then this ideal is just equal to the ideal generated by P. Okay, now what happens? Well, we know that we have a principal ideal. So R is a principal ideal domain, so I is principal. Okay, I mean, that's fine. How does that help us? Well, you kind of have to work things out. So I is generated by A and P. A and P are both in this ideal I. So we can write, they're both multiples of some common element C. So you can write A equals like C times C times R. And we can write P equals C times S. Okay, and now notice I've written this equation. P is irreducible, and I have a factorization of P. Okay. So in my factorization of P, either this is a unit or this is. So case S is a unit. Well, then C is equal to P times S inverse. In other words, C is an element of the ideal generated by P. So you can use this to show that actually the ideal I is actually generated by P as well. Or in other words, you know that P equals C times S, A equals C times R, but then A, replacing C by PS inverse, you see that A is equal to P S inverse R. In other words, A is an ideal in the first place. Okay, so if S is a unit, we're done. What about if C is the one that's a unit? Well, what we're saying is that, well, if C is a unit, the ideal generated by C has to be the entire ring. So then I is actually equal to R. Okay, what does that mean? Okay. Okay, actually, okay, I'll continue this after the break, but we're kind of like almost done, but I don't want to rush it. But what's gonna happen is that eventually we're gonna show, well, what's gonna happen is that we have the equation that we can write 1 as AX plus PY, and then we use that to show that, when we use that to show that we combine that with the equation that AB equals RP, and then we show that we're able to show that B is a multiple of P times something. Okay. So if S was a unit, then A is a multiple of P. If C is a unit, we see that B is a multiple of P, and either one of those is fine. Okay, so these steps, that'll be after the break, and then that shouldn't take long. And then we have examples, few examples. Okay, so yeah, let's start back up at, in 5 minutes. Okay. Any last? Okay. If you have questions, just maybe just ask them at the beginning of the next section. Okay, so let's take 5 minutes. Okay, bye.